Consider this reaction where you have two nitrogen monoxides reacting with two hydrogen gases to produce a nitrogen gas and two waters. The rate of this reaction is going to depend on the concentration of the reactants. If they don't collide with one another, the reaction can't happen. And if you increase the concentration of these reactants, you would expect the rate to go up. Right? You've increased the concentration, the collisions are now more likely, so the speed of the reaction is increased. But by how much? A rate law is an expression that allows you to determine how much of an effect changing the concentration has on the rate. So this is a generic example of a rate law. Rate is equal to a constant times some concentrations raised to exponents. The A and B in square brackets are reactant concentrations, and they have to be reactant concentrations because the rate of a reaction depends on the reactants, not the products. M and N are experimentally determined values that are known as reaction orders. And K is a rate constant that is specific to each reaction. The reaction orders are what tells you how changing the concentration affects the rate. These values are often whole numbers, but they can be fractional values as well. If your value of M or N is 1, that reaction order is known as a first order. And if it's 2, it's a second order. If it's 3, it's a third order, and so on. If the reaction order is 1, then the effect of changing concentration on rate is going to be linear. If you double the concentration, you double the rate. If you triple the concentration, you triple the rate. If your order is 2, you have a second order reaction order. And in this case, the effect of changing the concentration on the rate is now quadratic. So if you double the concentration, you quadruple the rate. And the same arguments can be applied for third orders or fractional orders. K is the rate constant for the reaction, and this value is going to be temperature dependent.